Okay, scholars, here we are in our last video over the rotation unit. I alluded to this a little bit earlier, but today we are going to go over the concept once again of equilibrium. So you guys already know, according to Newton's laws, what equilibrium is all about. Basically, you know that equilibrium occurs when the net force is equal to zero, and we have discussed in the past how two different things can happen when the net force on an object is equal to zero. First of all, remember that Newton's laws tell us that net forces cause acceleration or changes in velocity. So when the net force is equal to zero, there's no velocity change, no acceleration. And remember that that two things can be true when there is no acceleration. Our velocity may equal zero as well, in which case we have static equilibrium, or our velocity may be non-zero, in which case we have dynamic equilibrium. So these are just terms that you should be familiar with. Most important thing, everyone in here knows that when the sum of the forces acting on an object are zero, the acceleration is equal to zero, and that can be static or dynamic. Now, really I should be more specific and make this dimensionally specific. When the sum of the forces in the x direction are equal to zero, the x acceleration equals zero. So we do need to remember that whenever we are summing up forces, forces are vectors, and we do need to think about it one component at a time. So we could rewrite all of this, of course, for the y dimension, the z dimension, etc. But now that we know about rotation and the fact that torque can cause changes in rotational motion, and now that we've been analyzing that, we are able to write a new additional expression for a new requirement for an object to be at equilibrium. For an object to be at equilibrium, not only do the x and the y forces have to be equal to zero, but our net torque has also got to be equal to zero, which means that the thing does not rotate. This next statement I'm about to make is going to be key for helping you solve problems. Here it is, so please make sure that you get this down. And then all we're going to do today is just a whole crap ton of example problems to help you guys practice this. There's going to be a specific problem-solving strategy for these equilibrium problems I'm going to give you, and hopefully after we do the examples, you will get the hang of it. But here's the key that you need to understand to work out these examples. When an object is in equilibrium about a specific axis of rotation, it is in equilibrium about all other possible axes of rotation as well. So here's what I mean by that. You know that in order to identify and start calculating and writing expressions for torque, the first thing we have to do is identify an axis of rotation. So if we're looking at an object or a collection of objects that are in rotational equilibrium, if they are in rotational equilibrium, and they're in rotational equilibrium about a specific axis of rotation that we choose to analyze, as long as it's in rotational equilibrium, as long as this statement is true, that there's no rotational acceleration, then that object or that collection of objects or that system, maybe I should have said system here, will be in equilibrium, rotational equilibrium, about all other axes of rotation as well. We're going to see how this fleshes itself out to help us solve problems here in a little bit. But basically, this is pretty simple, pretty straightforward. It's not a brand new idea. For something to be in equilibrium, it means that there is no net anything, no net force in the x or y direction, and now we're saying it's also in rotational equilibrium. There's no net torque, and therefore we get objects that are not accelerating and not rotating. They have no rotational acceleration. This is really important for those of you who hope to go on to be engineers, like civil engineers. This is how like bridges get designed and built, things like that. You really want your bridge to be in static equilibrium, both translationally and rotationally. You don't want, if this is your bridge right here, you don't want this to become an axis of rotation and your bridge to start, swiveling this way or that way. That would be very bad. So civil engineers, whenever they're designing systems, buildings, bridges, roadways, etc., flyovers, usually they want that thing to be in static equilibrium. All right, let's go do some problems together. Before we do some example problems, I guess I really do want to give you the problem-solving strategy for equilibrium. It's really nothing new. It's what we've been doing for a while now. So the problem-solving strategy is this. Typically, you're going to start with torque first. It really doesn't matter, but you're going to look at your physical scenario, and you're going to just set the net torque equal to 0, and start deriving expressions for all the forces that could be causing possible torques in your system. This is probably the most complicated part of this. You can set your axis of rotation wherever is convenient to help you find unknown variables. This will become more clear when we start doing problems. But remember what I said on the last slide, that if this is true about an axis of rotation, it will be true about any axis of rotation that you choose. So sometimes it's helpful for us to choose an axis of rotation where certain forces do not cause a torque. Remember what's required for a torque. The definition of torque is R cross F. The force that's applied has got to be a distance away from the axis of rotation, and because it's a cross product, the force has to have a perpendicular component to that R vector. So it's going to be helpful for us to sometimes set our axis of rotation. This torque expression is always written with respect to a specific axis of rotation. Sometimes it's going to be helpful for us to set the axis of rotation somewhere where a certain force doesn't cause a torque, and so it drops out of the equation, if that makes sense. We'll look at that in some examples later. And then, of course, we're going to set the net force in the x and y directions equal to 0 and begin writing expressions for those. And then we're always going to be trying to find some unknown variables, so we want to try to write expressions that will help us find and solve for those specific unknown variables. Usually, wrapped up in all this, you're going to have 2 or 3 unknowns, in which case you will need 2 or 3 equations, so just keep that in mind. And remember that we analyze the x and the y directions, those dimensions we analyze separately. So just like this, you're going to have to build 3 at most. Sometimes you will not have to use all of these, but at most you're going to have to build 3 different equilibrium expressions and start fleshing out the left side of these equations. All right, so the strategy is just apply the concept of equilibrium in all dimensions and rotationally, translationally, and then just start trying to solve for those unknown variables. The only trick is knowing where to set your axis of rotation so it's convenient to start solving for your torque expression. And we're going to practice that. All right, so let's do some examples together. Okay, Throckmorton makes his return in these questions. Your cousin Throckmorton is balancing the end of the plank, which itself is balanced on 2 sawhorses. See the figure below. I guess I should probably draw the figure below. So here's my 2 sawhorses. Here's the plank. And here's my cousin Throckmorton. Let's see. Let's say that the mass of the plank is 90 kilograms. And it's a uniform plank. Let's say that the length of the plank is 6 meters. And let's say that these sawhorses are separated by a distance d. And let's make d 1.5 meters. I want to know, in order for Throcky to just be able to pull this off, to just be able to balance here at the end, what his mass needs to be. All right. So I need to recognize that this system and all of its components are in a state of equilibrium. That these statements then are true. The net torque is equal to 0, and the net force in the y dimension is equal to 0. Right away I can see I'm not worried about any forces in the x dimension horizontally because there are none. So these are going to be my guiding principles. What I want to do now is start fleshing out this net torque idea, that the net torque is equal to 0, and I'm wondering where I should choose my axis of rotation. Well, in order to answer this, we kind of have to get a perspective on the situation and on the question. We're looking for what needs to be true for Throckmorton to just be able to pull this off, what his mass must be. So, in other words, what is the maximum mass he can have? If he's 0.00001 kilogram more than that, this whole thing is going to tilt. So right now the system is like just wanting to start rotating and tilting this way. And if that's true, if it's just wanting to rotate like that, if the plank is just wanting to tumble and rotate clockwise, then here's what I'm thinking. I'm thinking that right here, the plank is just starting to lift off of this sawhorse. So it's no longer in contact with that sawhorse. In other words, I'm not really worried about that sawhorse. There's no contact between the plank and the sawhorse. Does that make sense? Because I'm looking for how Throckmorton is just able to pull that off. So if I start to draw a free body diagram for this, and this should always be the first thing that you do really is draw your free body diagram, I recognize that I'm not going to be worried about a normal force over here. Okay? So let me draw my free body diagram right here. Okay, so my free body diagram for the plank. I know that Throcky is contacting it right here at the end, so force of contact. And that force of contact is going to be equal to Throckmorton's weight, right? He's weighing down onto it. In other words, I know that the plank contacts through a normal force up on Throckmorton, so Throckmorton has to push down with the same force. So we could call this a normal force as well. That's going to be equal to the mass of Throckmorton times little g. I know there's a normal force right here. And what other force is there? Well, the plank itself has a weight, doesn't it? And where does gravity act to pull down on the plank? Yeah, gravity is always going to act on a thing as if it's acting on, as if all the gravitational force is on the center of mass. That is the simplest way of thinking about it. So where's the center of mass of this plank? The center of mass of the plank is going to be right here in the middle, isn't it? The very middle of the plank. And based on my diagram here, this is the right sawhorse, which is to the right of the middle of the plank. So I know that the middle of the plank is like right here. So here is going to be the force of gravity acting on the plank, which is mass of the plank times little g. All right. So where would we want to set our axis of rotation that's convenient for us? We have an infinite number of possibilities. I could set my axis of rotation at any point along the plank, but I want to choose a convenient location that like gets rid of some variables that I don't need. Well, it looks to me like I can set the axis of rotation right here where the sawhorse is. I can set the axis of rotation there. Because if I do that, then this normal force does not cause a torque, and then I am not worried about it. In other words, I actually know what the mass of the plank is. I know what little g is. Here's my unknown mass of Throckmorton. I would like to not bring another unknown, not bring the normal force into my expression. I could, but I would like to not. And therefore, I can choose the axis of rotation to be right there where the normal force is acting. And therefore, I can say that the torque due to the normal force is equal to 0, because remember, a torque requires that a force is some distance away from the axis of rotation. So the r vector for the normal force is 0, because the normal force is acting at the axis of rotation, so it's not causing a torque, so I can ignore it. All right, so this is what I was referring to earlier when I said that you need to think about where to choose your axis of rotation based on what you're trying to solve for and what's convenient for you. Okay, later I can show you that we could actually move our axis of rotation somewhere else and still solve this question, but it's just going to take a few more steps. So I need to write my net torque expression. So I know that there's torque due to gravity plus the torque due to the contact force of Throckmorton equals 0. And I want to flesh these out. The torque due to gravity, we need to think about direction here with torque. It looks like gravity is trying to pull down. Here's my axis of rotation. Gravity's pulling down to the left of it. That would cause the thing to swing counterclockwise. And here's Throckmorton's contact force. It's trying to cause the thing to swing clockwise. So remember that typically we say counterclockwise stuff is positive for torque. So I'm going to consider this force of gravity to be causing a positive torque. So my torque due to gravity is going to be the mass of the plank times little g times the r vector for gravity right here. Those are at 90 degrees. So remember, cross products are worried about the sine of the angle, and the sine of 90 is 1. And then the torque that Throcky over here is trying to cause is trying to cause the thing to rotate clockwise. So I'm going to consider it a negative torque. So minus the mass of Throckmorton times gravity times the r vector of Throckmorton. Or maybe I should say the r vector of this force, the contact force. You guys get the idea. That equals 0. So now it actually looks like I don't even need to analyze the forces in the y direction, because the torque equation here gets me everything I need, doesn't it? I know the mass of the plank. I know little g. I can figure out these r values, and therefore my only unknown in this equation is the mass of Throckmorton, and that's what I need. I needed an equation that gave me that one unknown. So now I'm going to be able to solve for this. So let's try to figure out what these r values are. So I'm going to go back to my physical diagram over here. This was my axis of rotation right here. And so how far away is gravity acting from that? Well, I know gravity's acting right here in the middle. And I know that the distance of separation between the two sawhorses is 1.5. And the sawhorses are like oriented right in the middle. So here's the middle of the thing. So how far away is the force of gravity acting? Well, that's going to be d over 2, isn't it? Halfway between the two sawhorses, or 0.75. So that's going to allow me to flesh this part of the equation out. The mass of the plank is 90. Little g is 9.8. And Rg is going to be 0.75. That value came from my understanding of the physical situation, that the center where gravity is acting is 0.75 away from the axis of rotation. And again, the axis of rotation I'm considering is on this sawhorse. All right? And remember, I'm not worried about the normal force from this sawhorse, the left sawhorse, because I'm saying that the plank is just not in contact with it. Okay, keep fleshing out my equation. Minus the mass of Throcky times 9.8 times his r, and that's going to be his distance away from the axis of rotation. Well, what do I know about where he's located? I know he's located at the end. And I know that the end the whole thing is 6 meters. So I know that from the exact middle to Throckmorton must be 3 meters. So how far is he away from the axis of rotation from this sawhorse? Well, I know that the sawhorse itself is 0.75. This right here is 0.75 away from the middle. It was half of this value. That's where we got this, right? So I know that Thraki is over here at the end, a total of 3 away from the middle. So he must be 2.25 away from the axis of rotation. Yeah, so this RT value right here, the distance away that Throckmorton is from the axis of rotation is 2.25. And again, the angle between those is 90, so I'm not really worried about the cross product there. So please make sure that you understand this diagram and where I get these numbers from. I know that the very center of the thing is right here, and I know that the sawhorse is, if the sawhorses are 1.5 meters apart from each other and they're symmetrical with the center of the thing, of the plank, then I know that this distance here has got to be half of that, 0.75. That's where this came from. And then if Thraki is 3 meters, I know that his distance from the axis of rotation must be 3 minus that 0.75, or 2.25. Okay, now it's just simple algebra to rearrange this and solve for the mass of Throckmorton. I'll let you guys do that on your own. It's pretty simple. But when you do that, you get that the mass of Throckmorton is 30 kilograms. So he's a little guy. He must be like some little punk kid. 30 kilograms, just like that. All right? And again, we did not even need to come up here and write a second equation for the forces in the y direction because the torque expression got me everything I needed. So one more time, let me explain and go through what we did. We set up our equilibria expressions, and then we started fleshing them out. And the most complicated part of all this is figuring out, for this torque expression, where's the axis of rotation going to be? And we said that it's going to be most convenient for us to set the axis of rotation at a point that will give us, in our torque expression, the fewest unknowns. And by setting it at this point of application of the normal force from this sawhorse, I'm able to eliminate that. That is not causing a torque, so I don't care about it. Okay? Now, we could have done this another way. We could have said that that a possible axis of rotation was the other sawhorse or something like that. So let's see what happens when we do it that way. Okay, so now I'm going to set this sawhorse's location as an axis of rotation. And once again, we can do that because remember that whenever you're in equilibrium with respect to one axis, you're in equilibrium with respect to all axes. So I can shift the axis of rotation wherever I like. I'm going to just draw some forces on here real quick. I know that gravity is acting on the plank right here. I know I have a normal force up right here. And I know that right here I have a force of contact from Throckmorton, which is just equal to his weight, the mass of Throckmorton times little g. So now when I go to write my torque expression, it's going to be a bit more complicated. Because now I am analyzing how all these forces are interacting with this axis of rotation. So remember that torque is R cross F. So I've got to figure out how long all these R vectors are. I need to figure out this R here. I need to figure out this one, how far away is the normal force acting, and then of course how far away is Throckmorton acting. Well, I guess before I do that, let me think about the directions of the torque. It looks like that both of my gravitational torques, the contact torque from Throckmorton sitting on the thing, which is his weight, and the force of gravity down with respect to this axis of rotation on the left sawhorse, they would both be trying to get the thing to swing around like this, so clockwise. Therefore, I'm going to count them negative. And it looks like this normal force would be trying to get the thing to swing around counterclockwise. So I'm going to consider that to be positive. So right away I'm going to say, okay, the torque due to the normal force minus the torque due to gravity minus the torque due to contact. This is my contact force because Throckmorton is contacting as he's sitting on the plank. It has to equal 0. So now I just need to flesh these out. So let's do this one first, the normal force torque. We know that's the force as a cross product with the r vector, which is just the distance right here. And that's easy. We know that the sawhorses are 1.5 meters apart. We were told that information earlier. I know that's a right angle. So the torque due to the normal force from this sawhorse must be the normal force times 1.5 minus the torque due to gravity. That's going to be right here. So that looks like the mass of the plank times little g times this distance. Do you guys remember how far that was? Well, the sawhorses are 1.5 meters apart, and they're symmetrical about the center of the plank, and gravity pretty much acts at the center of the plank. So this distance right here was 0.75 minus Throckmorton's contact force causing a torque is going to be the mass of Throckmorton times little g times his distance. And this time it's going to be, we know he's 3 meters from the middle, and once again the middle is right here. And the middle is 0.75 meters from this sawhorse. So we know that his distance away from the axis of rotation is 3.75. And you can see right away that now I have two unknowns in this expression. I have the normal force and the mass of Throckmorton. So I need another equation, don't I? The second equation that I need before I can start solving for this is to do a translational equilibrium analysis. The sum of the forces in the y direction equals 0. And the sum of the forces in the y direction, this is much simpler. I have gravity on the plank going down. I have Throckmorton's contact force going down. And I have the normal force here going up. So I can say that the normal force up minus mpg minus the mass of Throckmorton g has got to equal 0. Therefore, I can say that the normal force is equal to the mass of the plank times little g plus the mass of Throckmorton times little g. And now you can see what I have done. I have put one unknown in terms of another unknown. So now I can plug this in right here and start solving. So this is more complicated, but still doable, still solvable. I'm not going to solve it. You'll get the exact same answer, but I wanted to go through this just to show you that sometimes by wisely choosing your axis of rotation, you can make the problem much easier for yourself. Last time I chose an axis of rotation right here on that sawhorse because the normal force acting on it then dropped out of my torque expression. I didn't care about it. It wasn't causing a torque about that axis of rotation because it was not a distance away from the axis of rotation. And that made everything much easier for me because then I only had one unknown. By setting my axis of rotation on the left sawhorse, though, I had two unknowns, and so I had to come and do this analysis to get a second equation. All right? There is another way of doing all this using center of mass. So maybe some of you are recognizing that this seems kind of similar to a center of mass type problem, where the centers of masses are kind of balanced out, and we can indeed do that. But I don't want to take the time to do it here. If you're really interested, maybe we could do a one-on-one video chat at some point. Okay, let's go do a second example. All right, problem number 2. Throckmorton is back at it again. Oh no, Throckmorton, you are making poor life decisions. Committing a misdemeanor by breaking and entering into the Magic Wiggly Twisty Fuzzy Worm Toy factory. So, I guess, you've got to get your fix somehow in these trying times. I get it, Throckmorton. You need what you need. To do this, he's going to climb a 5-foot-long ladder. And we know that the ladder is 5 meters long, and it's making this angle theta 55 degrees with the ground. And it's resting against the wall, the frictionless wall of the Magic Wiggly Twisty Fuzzy Worm toy factory. Throcky, who weighs 800 newtons, makes it 1/3 of the way up the ladder before he hears, oh no, police sirens in the distance. So he's like right here. So let's think about this analysis. We know that he's in equilibrium. We know that the ladder is in equilibrium because it's not moving, it's not slipping, rotating, sliding, anything like that. And so we are interested to know what the coefficient of friction is at the base of the ladder down here. And that's the first question. And then we want to know the total contact force between the ground and the base. So what is the force of contact down here as well? So to do this, very first thing we got to do is draw a free body diagram. And this one's going to be a little bit complicated, but I think that we can do it. So here's my ladder. Here's the ground. I know that I have this angle theta, where theta is 55 degrees. And what forces are acting on the ladder right now? Well, of course, the ladder has a mass, 18.4 kilograms. And we know that the force of gravity is acting at the center of the ladder. And I know that's going to be equal to the mass of the ladder times little g. What other forces are there? Well, I know that Throckmorton has made it 1/3 of the way up, so this gravitational force acts halfway up the ladder, the 5-meter-long ladder, and Throckmorton only made it 1/3 of the way up, so Throckmorton, right here-ish, I know is exerting his own contact force on the ladder, his gravitational force, his weight weighing the ladder down. And I know that that's equal to the mass of Throckmorton times little g, which is his weight, and they actually give us his weight is 800 newtons. So I know right away that that's 800 newtons. Now, there are 3 other forces acting on the ladder. I want to see if you guys can think about what they would be and try to draw them on your own diagram. So pause the video and see if you can get the 3 other forces acting on this ladder. All right, well, first of all, right up here, right where the ladder touches this wall, there's no friction there because it says that it's resting against the frictionless wall. I guess that the Magic Wiggly Twisty Fuzzy Worm Toy Factory people really want to protect their property, so they engineered a frictionless wall to make it more difficult to climb up. But that's not going to stop your cousin Throckmorton, is it? Well, it's resting against the wall, though, so even though there's no friction up or down, I know that there is a normal force out right here. I'm going to call that the normal force at the top of the ladder, coming from the wall. I could have called it the normal force from the wall, of course. What else is there? Well, I know that down here where the ladder touches the ground, there's also a normal force there, isn't there? Remember, normal forces are always perpendicular to the surface of contact. That's why this one's coming straight out, because the ladder edge is right against the wall. So the normal force is just like that. And the ladder bottom would be right here. So the normal force from the ground would be going straight up, wouldn't it? So I have a normal force, and I'm going to call this one the normal force at the base of the ladder. And then who knows what other force I have? Yeah, I have a force of friction down here at the base, don't I? In fact, that's one of the things I want to find is the coefficient of friction between the ladder and the ground at its base. So which way is that frictional force pointing? It's either going to point left or right along the ground. So think about this. Which way is the ladder like wanting to slide right now? Well, I think that you can imagine that as Throckmorton climbs up the ladder is trying to slip to the left. So my frictional force down here has got to be pointing to the right. So there's my force of friction right there, going to the right. Okay, so now we want to know what the coefficient there must be. So think about what we're going to have to know in order to know the coefficient force. We're going to have to know something probably about this normal force, because remember that the force of friction is equal to the coefficient times the normal force. So if I'm asked to find something about the coefficient down here, I'm probably going to have to know something about this normal force. So what I want to do now is try to write some equilibrium expressions, torque and force expressions, that will allow me to eliminate unknown variables in a simple way to just leave one unknown variable. So what I really want to do is try to make the normal force here and the force of friction my unknown variables. And it looks like the other unknown that I have is this normal force up here. So I would like to analyze this from an axis of rotation where this normal force kind of goes away. In order to do that, I'm going to put my axis of rotation right here, in which case there is no torque from this normal force, and so I don't have to write it in my expression. Does that make sense? This is one strategy that's going to help simplify these problems for you, is to wisely choose your axis of rotation to scale down and eliminate down the number of unknown variables you have. So the first thing I'm going to do is write my torque expression about this axis. So I can see that I have, first of all, two gravitational forces. Those two gravitational forces, it looks like they're trying to get the thing to swing down this way, and that's counterclockwise. So I'm going to set them as positive values. All right. So I'm going to get the torque from gravity plus the torque from the contact force of Throckmorton. All right, so that takes care of these two. And then I have two more forces here. Let's see. The normal force, it looks like that is up, and it would be trying to get the thing to swing clockwise. So I'm going to subtract it away. So minus the torque due to the normal force at the base. And then the frictional force here, it is it's applied to the end of the ladder to the right. And that, of course, would try to get the thing to swing counterclockwise as well. So I'm going to add that one, plus the torque due to friction. I know that that has got to equal 0. So now I need to start getting expressions for all of these. And this time it's going to be a little bit more difficult because the angle is going to matter this time. All right? These forces are not acting perpendicular to the ladder. I'm going to come over here and write expressions for each of these. The torque due to gravity is going to be obviously the gravitational force, the mass of the ladder times little g. The mass of the ladder is 18.4. And then remember that the definition of torque, once again, is r cross f, where that r vector, I don't need to remind you of this, hopefully, is drawn from the axis of rotation to the point of application of the force. So this would be the r vector for this first one. And I know that the ladder is 5 meters long. So I know the length of this thing. This is the force of gravity acting on the ladder, which acts at the center of mass of the ladder. So I know that that is going to be 2.5. And then the cross here is cross product. So I know that that equals RF sine theta. Well, F is m times g. The length of r is 2.5. I need to think about this sine theta value, where sine theta is the angle between the vectors that I've drawn, okay? So the angle between the r vector and the force vector is going to be this angle right here, right? And I know that this angle theta right here is 55. So therefore I know that this angle, we'll call it theta prime, is 35 degrees, right? Because they're part of this right triangle. So I'm going to add in here the sine of 35. That's going to be the torque due to gravity. We can go ahead and get a number for that, make things simpler for us. Now let's find the torque due to Throckmorton about this axis. So I know his weight, his m times g is 800. His r vector, he only made it a third of the way up. So that means he's 2/3 from the end of this ladder here where my axis of rotation is. So that's going to get me 2/3 times 5 will be the length of that r value. And once again, he's making the exact same angle with it. So times the sine of 35. The torque due to the normal force. Here's my normal force right here. And so the torque due to that is going to be the normal force, which I do not know. I don't know that yet. Times its length away from the axis of rotation. It's all the way here at the other end of the ladder. The ladder is 5 meters long, so that's going to be times 5. Times the sine of the angle between those. All right. Well, it's going to be the exact same angle. These forces of gravity are pointing down. This force normal here is pointing straight up. So if I were to draw an r vector from the axis of rotation to the point of application of that force, it would be way down here. So the angle between those would be this angle here, which you guys can all see is also 35 degrees. So the sine of 35. All right. So there's the torque due to the normal force. And now I need to get the torque due to the frictional force. And I know that the force of friction is coefficient times normal. And then the cross product, anything about the sine of the angle between them. Let me draw this again because my diagram here is kind of jumbled. Here's the r vector. And here's the friction. And this is the angle that we know, right? 55 degrees. So this time it's going to be the sine of 55 will get me the torque. All right, so it looks like now I could plug all of this junk into this equation. Again, we're reminding ourselves that from the axis of rotation of the normal of this end of the ladder here, my gravitational forces are trying to get the thing to swing counterclockwise, so I counted them as positive values. The frictional force is trying to do that as well, so it was also positive. The normal force is the only one counteracting that. So I can go and plug all that into this. Okay, so here's what my torque expression simplifies to. I've just rearranged it, gotten all the positives on one side. I brought the negative force from the normal force over to the right. So you can see my problem. I have two unknowns, so I need another equation, don't I? Well, it looks like my other equation is going to come from analyzing the forces in the y direction. If I analyze the forces in the x direction, the forces in the x direction right now seem to me just to be the normal force at the top and the frictional force at the bottom, and I know those are equal to each other. That's not really going to help me. My unknown right now involves the normal force at the base, right? Maybe I need to specify so that you guys don't forget. This is the normal force at the base. So analyzing the y dimension is going to help me get that. Notice what I did. I thought about what I need to solve for, where my unknown is, and that guided me to think about what dimension I need to be looking at. So this is just simple Newton's laws. Looks like the only upward force I have in the y dimension is this normal force. So the normal force minus the 800 Newton contact force from Throckmorton's weight minus the weight of the ladder, mlg, is going to equal 0. And I can rearrange this and solve, and you guys could have jumped straight to this, recognizing that the normal force is the only one up, so it has to counteract both of these downward forces. And of course, I can solve for the weight of the ladder because I have the ladder's mass. It's 18.4. The normal force is equal to 980.32 newtons. That's the normal force at the base of the ladder. All right. So now I can come back up to my torque expression, plug that in, and actually solve for what the coefficient of friction must be. In other words, I have just solved for one of my two unknowns. I can plug it into this equation right here and solve for the coefficient, my other unknown. I'm going to let you guys do that. And your coefficient ends up being 0.025. Just like that. So one more time, let's analyze what we did. We wanted to know what the coefficient of friction was down here at the bottom. So we recognize that to know something about that, we're going to have to know something about the normal force right here. So we wanted to write a torque expression that had those in it and that eliminated any other unknowns that might be hard for us to solve for. And so the unknown that we eliminated was this normal force here by setting the axis of rotation here. So then I had 1, 2, 3, 4 torques that I established. The weights being positive torques because they were trying to cause counterclockwise rotation, and friction being positive, and the normal force here being negative because it's trying to cause clockwise rotation. And then I just went and tried to set up an expression for each of them. Remembering that torques are the cross product of R cross F. So, for example, the force of gravity on the ladder, here's my F, the force of gravity. And then R is the distance from the axis of rotation to that force, 2.5 meters. And then the cross product says to worry about the sign of the angle between them. And I recognize that the angle between these two is the same angle right here, which, because I know the angle from the ground is 55, I know this angle has to be 35, just like that. So doing that analysis allowed me to actually solve for the torques due to my weights, the weight of the ladder, the weight of Throckmorton. And then I came down here and I did the exact same thing for the normal force and the force of friction. Please be careful with your angles. Make sure that you understand where I'm getting these angles from. It's the angle between the r vector, where the r vector is drawn from the axis of rotation to the point of application of the force. Really, it's the angle between the ladder surface and that force. Okay? That allowed me then to write a torque expression. I recognize I had two unknowns, coefficient of friction and normal force. And then I saw that I could analyze the forces in the y dimension to easily solve for the normal force, because I recognize that the normal force down here must counteract both forces of gravity. And so I found the normal force, plugged it back in, solved for the coefficient, just like that. All right? I believe that there may have been an easier way of doing all of this, or at least an alternative way. We could have taken our axis of rotation down here at this bottom, and then we could have solved then for only 3 torques, the torque due to gravity, and then this normal force would have been a torque. And then we could have done an analysis in the x dimension where this force is equal to the force of friction, and then in the y dimension where, once again, this normal force is equal to the forces of gravity. That would have been another way for us to do it. So there are multiple ways of going about this, and one way might not necessarily be better. I just recognize that, hey, if I set my axis of rotation right here, then I can eliminate this unknown. Okay? All right, so part B now, find the total contact force between the ground and the base of the ladder. So what's that getting at? Well, I know that the ground is contacting the ladder in 2 different ways, through friction and through this normal force. So when it asks me to find the total contact force, it's asking me to find the vector sum of those. So for part B, I need to take the force of friction and do a vector sum with the normal force at the base. Of course, you guys know that a vector sum looks just like this. Tail to tip, force of friction, normal force at the base, and then this would be the vector I'm looking for, which would be like the total contact force or something like that. We know what the force of friction is. It's coefficient. I just found the coefficient times the normal force. I found the normal force earlier, remember? It was 980. So I know what the normal force is. Do vector addition, I'll be able to find the total contact force, and of course I'll get an angle there. Okay guys, so really simple vector addition just like we're used to, and of course don't forget to do some trig to get your angle there. Okay, so I hope you guys are getting the hang of what we're doing. Whenever we have problems like this, we have got to do two analyses, typically a torque analysis, setting our axis of rotation somewhere convenient, and then whatever kind of Newton's second law translational equilibrium analysis we need to do to get another equation to help us solve. Okay? All right, let's do another example. This time our cousin Throckmorton is pumping iron to get hella swole. Of course he is. A diagram of his stationary arm is given below. Let me give you the diagram of his stationary arm. So here's the weight he's pumping. And here's his forearm. Oh boy. And here's his elbow, and here's his bicep. Oh my. And his upper arm. Okay. So here's the idea. If you look at some anatomy of the arm, you got two bones in your arm here, and really close to your elbow, way back here, there's a tendon that connects from your bicep and upper arm muscles to your forearm. And that tendon like really connects very close to the elbow, but we're going to exaggerate the distance that away from the elbow that it connects. So we're going to model it the arm system like this. Here's his forearm. Let's say that his forearm from wrist or hand to elbow has a length of L. And let's say that right here is where he's holding on to that weight. And let's say that the weight just has a weight of W. So I'm kind of going ahead and drawing a free body diagram. Let's say here's his elbow back here. And let's say that the tendon, the support tendon that goes up, which again I'm exaggerating the distance, attaches to the forearm bones at some distance D away from the elbow. When it does so, it makes an angle theta, and it supplies a tension force up. Okay? So I'm going to call that tension force T. And let's say that it adheres to some part of the upper arm, muscle or bone of the upper arm, at a height of H. So it ends up attaching to the upper arm at a height of H. Okay? Just like that. Now there are also forces that are being acted on the forearm by the upper arm. In addition to the tendon, the upper arm muscle support structures itself supply forces on the forearm. And this is one thing that I'm trying to find. So two things I want to find in this question, and I'm not giving you any numbers, so it's all going to be in variables. I want to find the tension in the tendon, so I want to solve for T. And I want to find two components of a force exerted by the upper arm on the forearm at the elbow. So back here at the elbow, the upper arm, through muscles and support structures, exerts some kind of force in the X and Y dimensions. Now listen. I do not know what direction those forces are in. In other words, in order to lift this weight and get this system in equilibrium, the upper arm might be kind of pushing down on the elbow, or it could be pulling up on the elbow. I do not know. So I'm going to have to make a guess. And this is kind of what you should always do when you're questioning about the directionality of a force. Just make a guess. And if your direction is wrong, your answer will be negative, which means it's the opposite of what you guessed. Does that make sense? So let me redraw my forces here in res so that we don't get confused. And let's say that for now, let's guess that the upper arm exerts an upward force on the elbow. So I'm going to call this the force at the elbow in the y dimension. And now this question should be really easy. What direction does the upper arm have to supply a force to the forearm in the x direction? Well, think about this. This tension force is going up and to the right. That right force, that positive x component of the tension force, is the only x force I have in the whole system. So to be in equilibrium, I know that the force at the elbow in the x direction must be pointing left to counteract the right component of the tension force. Does that make sense? Okay, so what we need to do now is figure out where we're going to put our axis of rotation to try to eliminate as many unknowns as possible. I want to solve for three things right now. I need to solve for tension and the force exerted by the upper arm on the forearm at the elbow. I need to solve for these three things. Well, if I put the axis of rotation at the elbow right now, then that eliminates two unknowns and leaves me with just one unknown, which is going to be perfect for me. So if I put the axis of rotation at the elbow, then these forces that are acting at the elbow don't matter, right? They don't cause a torque. So now I can write a torque expression. It looks like I'm going to have the weight is trying to get the arm to rotate around counterclockwise, so I'll have that as my positive torque. And it is making a 90-degree angle with a line I could draw back to the axis of rotation, so I don't really care about the cross product. So the positive torque from the weight is going to be WL. I'm going to subtract from that the torque that the tension force is causing. That would pull the arm up in a clockwise direction, which we consider to be negative, and that's going to be the torque. The tension force, and then r cross theta. It's a distance d away from the axis of rotation at the elbow, and then it has it makes an angle theta, so sine theta equals 0, just like that. All right, so it looks like now I could rearrange and solve this for t, which is one of my unknowns. And I could just say then that t equals WL over d sine theta, just like that. Okay, now I want to try to figure out these other forces. And to do that, it looks like I simply need to do Newton's law translationally. So let's do the y dimension first. The sum of the forces in the y dimension equals 0. So my upward forces are going to be that force at the elbow in the y direction is going up. It looks like my y component of torque of this tension force is going up, and that's of course going to be t sine theta. And then looks like my weight force is going down. And so I could rearrange this and say that the y component of that force is my weight minus t sine theta. But I wonder if I could get t sine theta in terms of some other things. Well, if I go back up here to my tension expression, I know that T sine theta is equal to WL over D. Why would I want to do this? Why would I want to get things in different terms if I was fine with sine theta in my tension expression over here? Well, remember, we guessed about the direction of this y force. And right now, this is not really telling me, this expression is not really telling me if our guess was right or wrong. I want to put something maybe in terms of these lengths, these distances and lengths, because that could help me determine whether or not this force is actually supposed to be pointing up or down. So we can say then that if T sine theta is WL over D, then this force is equal to W, the weight force over here, the weight of the weight, minus WL over D. And I still cannot immediately see if this is going to be a... and now we can see that this gives us a negative answer. L is longer than D, right? L is longer than D, so L over D is some number greater than 1. So we're going to get W minus some number greater than 1 times W, which is going to give us a negative value. So now we know that our guess for the upward direction of this force that the upper arm puts on the elbow is wrong. The upper arm actually is pushing down at the elbow here. And that kind of makes sense that the upper arm would need to push down at the elbow because that helps to counteract the torque caused by the weight over here. So that does make perfect sense. We could get this in a more algebraically satisfying way. We could say this equals WD over D, just multiply this first W by D over D, minus WL over D. We could factor out a W. And we know that D minus L is negative. D was the short distance, right? D was the distance that the tendon is away from the elbow. And so ultimately, we could factor out a negative, and we could say that this force is negative L minus D over D. Of course, we did not have to do that. Any of these answers would have been sufficient. This last one is really the most technically correct answer. But anyway, we do see that it's negative. So I now know that this force in the y direction there actually points down. The upper arm puts a force down on the elbow right there. Remember the question asked us to find both the components, so I need to figure out what this x force is. And of course, we already said that it is the only force that is counteracting the x force of torque. So when I do my Newton's second law in the x direction, sum of the forces in the x equals 0. To the right, or positive, we have the x component of torque, of that tension force, which is going to be T cosine theta. And that has got to equal Fex. And we could be even more specific here. I know that my force of tension is WL over D sine theta. So I could say that Fex equals WL over D sine theta times cosine theta. And of course, that is equal to WL over D cotan of theta. And cotangent is 1 over tangent, right? And tangent is opposite over hypotenuse. So remember that up here, and I guess I could have incorporated this for the sine value, but the opposite side of this is h over the hypotenuse of T, the force of tension. So I plug that in there. I'm so sorry, that's not what tangent is. Tangent is opposite over adjacent, isn't it? So opposite is h over adjacent is d. Because it's on the bottom, I like that. That d comes up to the top. And it looks like the whole thing ends up being WL over H. That's a nice, neat expression for the force in the x direction that the arm has to put onto the elbow. And I suppose that maybe we could say that the sine of theta here is opposite over hypotenuse, which is h over t. Okay, so again, for this problem, the first thing that we wanted to do was identify an axis of rotation that let us solve for the unknowns the fastest. And by putting an axis of rotation here at the elbow, where these two forces do not cause a torque, that only left us with one unknown, the force of tension right here that was causing a torque. That's what we wanted to solve for in terms of other things. And so we were able to do that right away. And then we wanted to start solving for these components. First, we kind of guessed that this component of the force that is on the elbow was up, and so in the y direction we were able to make this expression, and then slowly we started to solve. We got to this very simply, but we recognized that was not enough to help us understand whether or not it was truly up or down. Then we got to these other expressions, which helped us see, well, actually, we get a negative value, which means our guess about the upward direction was wrong. It's really pointing down. Anyway, I really would not worry too much about the algebra in these problems. More, you need to understand the concepts and the problem-solving strategy, that we are always trying to get the simplest expression that's going to help us solve for what we're wanting to solve for. So the trick really is going to be finding what axis of rotation to use. All right, last equilibrium example. This one is classic. Got a wall with a meter stick, and it's held up against the wall by this light cord there. And we do have some friction against the we do have some friction between the meter stick and the wall. And we're even told what that coefficient value is. So the first question A, what is this angle theta between the meter stick and the cord? Well, I know that I have equilibrium, don't I? So what I might want to do is start drawing free body diagrams for this scenario. I'm going to do that now. Notice this is what I've been doing for all these questions, is drawing free body diagrams first. So very clearly I'm going to have a force of tension right here acting on the meter stick. I'm going to have gravity pulling the meter stick down, and of course that happens at the meter stick center, 0.5 meters. I'm not told the mass of the meter stick, so I'm just going to leave it m. I'm going to let the mass of the meter stick be m or something. What other forces would I have acting? Yeah, I have a normal force between the wall and the meter stick, right? That's going to be this way. And then I also have a frictional force between the meter stick and the wall, don't I? Friction always opposes relative possible sliding motion. And I can understand that this meter stick would probably be trying to slide down the wall, so force of friction is probably going up. Sometimes, guys, it is going to be difficult for you to know which way friction is trying to go in these questions. Just pick a way, and then if you end up getting a negative answer, you know that you picked wrong. When could friction go the other way? Well, maybe the tension force wasn't quite strong enough, or the force of gravity was really strong, or something like that, and therefore the meter stick would maybe be trying to rotate this way, which means that this end of the meter stick would be trying to instantaneously go up this way, which means the frictional force would be going down. So that is, I guess, technically a possibility, but probably here it's going to be a safe guess for us to say that gravity is just trying to pull the meter stick down, so friction is trying to push it up, just like that. So I want to find what this angle is, what this angle theta is. Just like always, we're going to start with a torque expression, but before we do that, remember what we like to do. We like to try to find an axis of rotation that's going to leave us with the fewest number of unknowns. Well, if I put an axis of rotation, for example, on this end of the object, that's not going to do me any good because the force of tension, which has the angle in it that I want, is not causing a torque. So that would be a really crappy choice for axis of rotation. What if I put my axis of rotation right here? Would that be a good choice? No, because then I have all kinds of different unknowns. I have a tension force as my unknown. I have a normal force as my unknown. I have a force of friction as my unknown. So those are not going to be great for me. So I thought it's going to be best for me to eliminate in my torque expression these two forces by putting my axis of rotation right there. All right. So this is a meter stick. It's a meter long, so we don't really have to worry too much about distances. I know that I have two forces causing a torque. I have a torque due to gravity here, and I have a torque due to tension over here. Once again, by putting the axis of rotation here, these forces are not causing a torque because they are not a distance away from the axis of rotation. And let's think about the direction. Gravity will be trying to get the thing to swing down this way. This tension force is trying to pull it up with respect to this axis of rotation this way. This tension force is counterclockwise, as we like to say, is positive. So I'm going to list it first. The torque due to the tension force is R cross F. It looks like R is going to have a length of 1 meter. This tension force is over here at the very end of 1 meter. It's going to have a size of force of tension, and it is going to be manipulated by the angle between those, which is this angle, sine theta. So one last time, torque is R cross F. My R vector has a length of 1 meter. The force is force of tension, and I'm worried about the sine of the angle between them. All right, so there's my positive torque, and it looks like my negative torque, trying to cause it to rotate clockwise, would be the torque due to gravity, where the R vector has a size of 0.5 because gravity is right in the middle of it, is acting right in the middle. The halfway through a meter stick is half a meter. The size of the gravitational force is mg, and then of course the sine of the angle there would be 1 because it is a 90-degree angle. So that equals 0. So I know that Ft sine theta is equal to 0.5 mg. Well, that is not enough information for me. I'm trying to solve for the angle, and right now I guess I kind of have two unknowns. I have the force of tension and I have sine of theta. So what I would like to do is try to get another equation to help me. And of course, to do that, we need to go into translational considerations. Typically in the past, we've gone to the y dimension, so I guess we could do that now. Let's think about the y dimension. I'm going to do this quite quickly because you guys should be used to this. Looks like my my upward forces in the y dimension are the force of friction, and of course force of friction is coefficient times normal, so 0.4 times the normal force. My other positive y force would be the y component of the tension force, which is Ft sine theta. And of course, once I rearrange, those have got to be equal to the downward force, which is mg. And this is not really helpful because I have three unknowns in this one: normal force, force of tension, sine theta. Even if I rearrange this to solve for Ft sine theta or something like that, I'm ultimately after that angle theta. So that's not going to help me. If I rearrange, solve for that, plug it back in, I've just eliminated sine theta when I'm after. So that's not going to help. I wonder then if we should go to the x direction. Looks like the only x forces I have are the normal force and the x component of the tension force. So the normal force then has got to be equal to the x component of the tension force, cosine theta. Aha. it looks like I could take this now and plug it in for the normal force right up here, and then maybe start rearranging some things. So let me do that. When I do that, I get that 0.4 ft cosine theta plus ft sine theta equals mg, and it's just an algebra game from here. See if you guys can figure out how to take this expression and this expression, rearrange them in some way, and solve for theta. Okay, so here's what I did. I recognize that ft sine theta is 0.5 mg, so I plugged that in right here, and that got me 0.4 ft cosine theta plus 0.5 mg equals mg, subtracted 0.5 mg from both sides, 0.4 ft cosine theta equals 0.5 mg. And then you really have several options, I guess, to solve now. But here's what I did. I recognize that I have two equations now that have two unknowns: force of tension and my angle. So I wanted to figure out the simplest, quickest, easy way for me to manipulate those two to solve for the angle and to get rid of force of tension. So what I did is I just divided the two equations. I recognize that sine divided by cosine is tangent. So I could take this equation, divide it by this one, in which case force of tension will cancel out, and I will get this, that 1 over 0.4 tangent of theta, I'm just dividing this by this, equals 0.5 mg divided by 0.5 mg is 1, and therefore I get that the tangent of theta must equal 0.4. And I can do a quick inverse tan in my calculator and find that the angle theta has got to be equal to 21.8 degrees. This is an algebraic trick that people forget that you have access to, just dividing the two equations. If I divide them, sine over cosine collapses to tan, ft over ft cancels out, 1 over 0.4. It was really simple from there. So this was a tricky question. There may be a simpler way of solving it, but I've not found it yet. As always, we first write our torques. Think about direction. The tension torque wanted the thing to rotate counterclockwise, so I counted it positive. The torque due to gravity would have it rotating clockwise, so I considered it negative. I rearranged. I recognized that was not enough. So I had to go to, and I remember the very first thing I did was I set my axis of rotation over here on the far left of the system to try to eliminate these unknowns. You could solve this by setting your axis of rotation elsewhere, but this, I think, is probably going to be the quickest, easiest way. Then the sum of the forces in the y direction, because it's an equilibrium and they equal 0, so I started doing that. Of course, I had one negative force and one positive force, the y component of tension. Excuse me, I had two positive y forces, didn't I? I had the force of friction here. And then I recognized that was not quite enough, so then I had to repeat the analysis in the x direction. And I saw that in the x direction I only had two forces, the normal force and the x component of tension, so they had to be equal to each other. That allowed me to kind of take the normal force then out of my equation, rewrite this y expression as this, and then just try to go from there. I recognized that I could get rid of ft sine theta because earlier I had solved it was this. And ultimately that allowed me to get two expressions that have two unknowns, my two unknowns being ft and the angle theta. And the quickest way for me to combine these two equations to solve for the angle theta was to cancel out the force of tension by dividing. And of course sine over cosine is tangent, and that allowed me to solve solve pretty nicely for that angle. All right. So let us press on now and find and do our next example. So in this one, we have a block that has the same mass as the meter stick. So remember, we were calling that M. Is hung from the meter stick at a distance x from the wall. Determine this distance. Everything else is the same. So here's my meter stick. Here's my cord. And I know that the block that I'm hanging is some distance x away from the wall, and that is what I want to determine. So what I need to do then is start trying to solve start drawing a free body diagram, kind of like I have always done. This angle, by the way, is yeah, I forgot to write this down in the problem. Sorry. The angle theta is now 15 degrees. Okay, so let me think about the best axis of rotation to begin analyzing our equilibrium for rotation. Well, I think I'm going to do the exact same thing. I think I'm going to let the axis of rotation be over here, just like that. And now I'm going to draw all my forces. I'm going to do this in red. So I know that I have a force of tension up this way. I know that I have two forces of gravity now acting on the meter stick. I have the force of gravity here from the box, mg. Now, I don't know where this thing is located. I do not know if it is to the right or to the left of the center of the meter stick. In other words, I don't know if it's position x. I don't know yet if x is greater than or less than 50 centimeters, 0.5 meters. Does that make sense? Really, I don't know where this thing is in my diagram. That's okay. I can still make a good diagram. I'm just going to guess that it's farther to the right. So here's the center, mg, the force of gravity acting on the meter stick itself. All right. So this mg here, this force is from the block hanging, weighing down the meter stick. Again, it has the same mass as the meter stick, so I can use the same variable m. And because I'm looking at things from that axis of rotation, those are all the forces I'm worried about for the torque. Now, of course, just like last time, we're going to have a force of friction up here, and we're going to have a normal force acting from the wall into the meter stick that way. Okay, so now my torques from this axis of rotation. Once again, we always have to think about direction. And once again, my force of tension is trying to get the thing to rotate counterclockwise, while these would be trying to get it to rotate clockwise down from this axis of rotation's perspective. So I'm going to consider those to be negative, this to be positive. And again, remember that torque, we're worried about three things. We're worried about the size of the force, how far away it is from the axis of rotation, and the angle it makes with the line drawn to the axis of rotation. So the positive torque from my force of tension is just very simply going to be Ft sine theta. It is 1 meter away from the axis of rotation. And then I'm going to get minus mg times 0.5. That's this one right here. Because that is halfway through. It's halfway through the meter stick from the axis of rotation, or 0.5 meters. And then minus mgx, where that x is what I'm trying to solve for, right? The distance that this box is away, the distance that the point of contact of this force is from the axis of rotation. That equals 0. Rearrange this, of course, and we're going to get that mg times 0.5 plus mg of x, mgx equals Ft sine theta. That's not enough. I have, once again, two unknowns. I know what theta is this time, but I don't know what the tension force is this time. So I have two unknowns. I need another equation. Where am I going to go to get that? Why don't we go to the y component? Sum of the forces in the y direction equals 0. My two upward forces are the force of friction, which is going to be coefficient times normal, plus the y component of tension, which is Ft sine theta. And then, of course, my two negatives are minus mg and minus mg, so minus 2 mg, that equals 0. And I could, of course, rearrange this to say that my positive forces have got to be equal to my negative force, or my downward force. The sizes of those must be equal to each other. Okay, so I wonder now if I could pause here and try to figure out a way to start solving for all of this. Well, I have another unknown that I brought in, don't I? I have the normal force. And I believe this is similar to what we did last time, where we said, okay, to understand what that must be, let's do an analysis in the x dimension. Only two x forces, right? The normal force and the x component of the force of tension, which must be equal to each other. Okay, so then I can rearrange this y expression and say that coefficient times ft cosine theta plus ft sine theta equals 2 mg, just like that. And it looks like here I could take my y expression. So basically right now, I hope you guys understand, I have two equations with two unknowns. The x is my unknown and the force of tension is my unknown. This time, so last time, remember, I just divided the two equations. This time it's not that simple because my force of tension is kind of split up here amongst these two. So you're welcome to do whatever you would like. You can factor out a force of tension and then maybe try to divide them. That would be a good way of going about it. Here's what I did. I factored out the force of tension from this expression, and I got it equal to things that I do know. I know mu, I know the angle theta, right? So I was able to say that the force of tension, I just factored it out, times mu cosine theta plus sine theta equals 2 mg. Therefore, I was able to say that the force of tension equals 2 mg over mu cosine theta plus sine theta. Now I have an expression for the tension force, which I can plug in right there, and I'll be good to go to solve for that x value. So I hope you guys are appreciating the pattern, the problem-solving strategy for these types of questions. Draw your diagram. Draw your free body diagram. Start with torque. Pick an axis of rotation that helps you eliminate the most unknowns that you can. Start writing your torque expression. Don't forget the definition of torque. Don't forget that the angle between those vectors matters, just like it does right here. Don't forget the direction matters. Think about the way that force is trying to get the thing to rotate. Counterclockwise is positive, clockwise is negative. So think about directionality. If you have two unknowns in your torque expression, you're going to have to go to a Newton's second law for translational motion, a translational equilibrium expression, and then keep going until you can combine some equations. All right? I will let you guys try to solve this. All right, here's my equation that I eventually got for x right here. Again, that's just me rearranging these two. I solved for force of tension, put it in terms of other things, and then I was able to plug that into my torque expression, and then my only unknown became the x value. I know what the coefficient is. My mass canceled out. I had a mass in every single term, so I was able to cancel out mass, subtract 0.5, and then I was able to solve for x that way. So when you do that, you get an x equal to 0.302 meters. So our guess was wrong. It doesn't matter at all. It doesn't change my diagram or what's happening. but my x value has the thing being less than halfway, so over here. All right. Okay, so I hope you guys are appreciating the problem-solving strategy for these equilibrium problems. Equilibrium. Now we're saying that the objects have to be in rotational equilibrium, where the net torque is 0, and translational equilibrium, where the y and x components of the forces are balanced as well. And remember what this means. It means that the acceleration and the angular acceleration are equal to 0. Every problem we looked at was static equilibrium, where the velocities were also equal to 0, but that may not necessarily be the case, right? All this tells us is that the thing has no acceleration translationally or rotationally. Okay, I hope this was helpful. This was our last concept in rotation, and really it's no different than what you've done before, analyzing forces, just a little bit more complicated now with torque. We will practice this, and this was our last unit that we need to know before the AP exam. So we're going to start reviewing, and we'll take an exam over this unit. But I hope this was helpful for you guys to get the hang of the problem-solving strategy for solving these equilibrium problems. All right, y'all. Thank you.